Okay, we're going to continue on here, chapter 17, I think. So we were talking about electrochemistry last time, and really we spent most of the time, I think, going over redox reactions. And again, it is oxidation and reduction reactions. They do occur together. So if somebody gets oxidized, there will be somebody get reduced. Really, the main kind of two definitions that we use pretty much in general chemistry for oxidation is, again, somebody that loses electrons, while reduction is somebody that will gain those electrons, essentially electrons being transferred in that sense. We also have our oxidizing agent, and that is the substance that gets reduced. We also have our reducing reagent, our agent, and that is a substance that gets oxidized. And again, they're called that because they do cause sort of the opposite effect in the other substance. Remember, you could follow the oxidation numbers and just use a basic number line to sort of figure out what is happening in terms of oxidation and reduction. Again, if you look at the oxidation state or number of a substance on the left versus on the right, and it's moving in a positive direction, that means that it is losing electrons and becoming more positive and going through oxidation. Again, if you look at the oxidation state and it's sort of moving kind of to the left here on the number line, becoming more negative, that guy is going through reduction. So that's a very kind of simple way to figure out what is being oxidized, what is being reduced. Again, being able to assign oxidation numbers is really important, so you can figure these things out, which will be important in what we're going to talk about here today as well. Remember that pretty much anything in a standard state has an oxidation state of 0. Oxygen is usually a really good place to start. It has a -2 oxidation state unless it's peroxide. Things like hydrogen will be +1 unless it comes after a metal, will be -1. When we add up all of our oxidation numbers, they do need to equal the overall reaction, the overall charge on that molecule if there is one. So if it's neutral, it needs to equal 0. If not, then obviously it needs to equal whatever the charge may be. We talked about balancing equations in acidic and basic conditions. And again, the idea here is we have our half reactions, and this would be our oxidation half reaction. Thank you. Where we have our electrons there on the product side, like they're being given off. We would also have perhaps our reduction half reaction, where the electrons are on the reactant side. If it's just a simple sort of half reactions, we would add these back together. The main thing you have to make sure is, again, you have the same number of electrons in both half reactions. They should always be added to opposite sides. Now, if we're doing acidic or basic conditions, we do split off the half reactions. We balance all elements except hydrogen and oxygen. Once we balance all the other elements, like normally just put in a coefficient in front, we then balance oxygen with water. And again, we add a water to the side that needs oxygen to balance it out. And every time we add water, though, to the opposite side that we add the water, we do need to add 2 H pluses. Again, that way you won't be short hydrogens when it's all said and done. At that point, we could add our electrons. And we're going to add our electrons to balance the charge on each side. And remember that the charge on each side of these half reactions do not need to be 0, but they do need to pretty much just have the same number. We then could add our half reactions back as long as we have the same number of electrons in each. And if we do not have the same number of electrons in each, we then would need to multiply each half reaction maybe by a constant number or one of the half reactions by a number to do that. And if you do all that, should then be balanced in acidic conditions. And at that point, if you want to turn it into basic conditions, you will have some H plus in your equation, which tells you it's acidic. You would then add an equal number of OH minuses to both sides. And the side where we have H plus and OH minus together, they will combine to make water. You usually will then be able to kind of reduce down some of the waters that's there, and you'll be left with an equation that has some hydroxide in it. And then you'll be balanced in basic. So that's probably the simplest way to kind of go into basic, which is basically just do it acidic, and at the end, kind of turn it into a basic conditions. As I mentioned before, you could do it earlier on, add the hydroxide before you add the electrons, but it does get a lot of sort of reducing down and things sort of canceling earlier on. Any questions on any of that stuff there? So clearly you need to be able to identify things that are being oxidized, things that are being reduced, things that are oxidizing agents, reducing agents. You need to be able to balance, obviously, these type of redox reactions in acidic and basic conditions. Any questions on any of that there? All right, then let's get into really kind of the heart of what's in this chapter, which is a galvanic cell. And a galvanic cell is essentially a redox reaction that's happening. There's an oxidation and a reduction side to a galvanic cell. So this is one that you could traditionally build in the laboratory, although nowadays, I guess we kind of do still a little bit, not as much build it like this. So there are different parts to a galvanic cell. We have on this particular example here on the left-hand side, we have what is known as the anode. And the anode is where oxidation occurs. And basically, electrons will come out through the wire, which connects both sides of the galvanic cell. And it will go to the other side here, which is the cathode. And the cathode is where reduction occurs. So the anode is where oxidation occurs, and the cathode in a galvanic cell is where reduction occurs. So essentially what's happening in this case is, for example, here we have zinc, and we have a solution that has zinc ions in it, and our solid guy here is zinc. And when zinc loses electrons and goes through oxidation, it's basically going to jump out of the solid and go for a swim into the liquid. So basically it's going to go from kind of the solid and then jump into the liquid part of it there and go for a swim. Its electrons will come out here. And by the way, electrons can be used to do some type of work, kind of like a battery. If you look at your battery compartment, right, the little wires there and stuff like that is pretty much what is happening there. You get some voltage there as it goes through. And it'll come to the other side. And when it comes to the other side, in this case, we have a copper solid electrode, and we do have a solution that contains copper in it. So when those electrons come in, they're actually going to grab some copper ions that are floating around in the solution. It's going to reduce them, and these guys are going to come out of the swimming pool and basically become solid in this case. So we have basically our guys on the left there, as they get oxidized, will become ions. Ions are typically found in solutions, so they jump into the solution. Those electrons then travel through the wire to the other side, where they will reduce down the copper ions that are swimming around in the solution and allow those guys basically to step out. Now, another really important sort of aspect of this is the salt bridge. And the salt bridge here is basically the guy that sort of completes the circuit. It kind of connects both the anode to the cathode. It is usually filled with some type of salt solution, like we see here in this example, potassium chloride. You put a little plugs usually in it, cotton a lot of times, but it still allows sort of the ions to flow in and out, but doesn't allow everything to just drop out, obviously, of it. And in this particular case, as you can see, we have some negative chloride ions heading in this direction. We got some positive potassium ions heading in the right-hand direction. So there is, as we talk about here, sort of a potential difference between the anode and the cathode. You could think of it as sort of like more positive there on the cathode side. And that's really good because that's going to kind of pull the electrons which are negatively charged towards that sort of potential difference, right? Opposites attract. So that's going to allow the electrons to want to kind of go towards the cathode side. And the result of this is we will get our half reaction. So we have our zinc that basically is going to drop a couple of electrons here and go for a swim. And that is our oxidation half reaction, going from 0 to +2, again, becoming more positive in this case. On the right-hand side here, we will have our copper-2 that's swimming around. We'll pick up a couple of electrons, and we will end up with a solid copper there on the right-hand side, which is our reduction reaction. And again, this is going from +2 to 0. So if you look at the little number line situation, starting at +2, ending at 0, becoming more negative and going through reduction, while over here our zinc starting at 0, going to +2, becoming more positive, so going through oxidation in this case. When we add it back together, we get the overall reaction that we see on the bottom there, which is, again, our zinc going from 0 to +2, and our copper going from +2 to 0 in this particular case. So the idea here is, in a galvanic cell, we could use those electrons to do some type of work, power something, as we kind of use those electrons as it goes from the anode to the cathode. Now, why is the sort of salt bridge really important for this functioning of the galvanic cell? Well, the idea here is, let's just maybe redraw it here. We have zinc and copper. So we have this cell basically, and on this side here, we got some zinc, and we have some zinc solution there. I think they use sulfate flowing around, connected, no voltage. Down to the other side, where we got some copper, maybe a beaker to put it in would be good. There we go, copper 2. I think they use sulfate too, did they? They did. And we got sulfate thrown around in here. And again, we have our salt bridge there that is basically connecting the two. And again, we get this nice flow of electrons, again, coming from our anode to our cathode in this particular case. So what would happen in this case if we basically just took out our salt bridge? So if we just took out our salt bridge, for example, here, take it out on both sides. There we go. What's going to happen is, as this cell starts to run, as I mentioned before, when this zinc gets oxidized, they're going to basically jump into the solution. So as it does that, you're now going to be adding to this solution a lot of zinc ions that are positively charged. Now, on the other end, we have a lot of these positive guys here in the solution is actually going out of the solution as they get reduced. So they're going to come out of the solution, which means essentially you're going to have a buildup of negative charge over here. So as you run this cell without your salt bridge, you're going to get this buildup of negative charge because you're taking out all of the positive ions on the right-hand side. And you're going to get this buildup of positive charge over here on this side as you're dropping in all of these zinc ions. That is not so great with my negatively charged electron, because now my negatively charged electron's not going to want to come over here because that's a big old negative, right? And it's actually more positive over here, so there's no incentive for the electron basically to travel across the wire. It's going to sit here. Your cell pretty much is going to stop. You're going to get no voltage, right? Because you got that buildup. It's preventing really those electrons from going to the other side. So the essential function of the salt bridge is to allow for that buildup not to occur. So when we insert our salt bridge in here, for example, which is a good idea in most cases, and as we saw there in the picture, they use potassium chloride. The potassium ions and the chloride ions, it's going to send some chloride ions over here to the left. And what that's going to do is pretty much stop that buildup of positive charge over there. It will send these positive ions over here to the right, which will stop that buildup of the negative charge. And now you'll have sort of the right balance here on the cathode side versus the anode side, to again allow your electrons to start to flow. So the salt bridge, although it doesn't seem like maybe it's all that important, it is really important because without it, you'll get the buildup of charge where you don't want it to happen. So you happen to have the buildup of positive charge where you don't want it and a negative charge where you don't want it. So it keeps really the charge under check in both parts of the galvanic cell. And that's going to allow really this side over here to be a little bit more positive and kind of pull those electrons over. Any questions on the salt bridge there? All right, so you do need to know, obviously, the different parts of a galvanic cell, the anode, the cathode, how the electrons flow, the purpose of the salt bridge. In a spontaneous process, we typically get positive voltage. It's typically what we want, and that's usually what we want to happen. It's essentially like putting your batteries in your device correctly. Put your batteries in your device backwards, things don't work because you just made your spontaneous process non-spontaneous by flipping everybody around. So I talk a little bit about batteries as we go through this, just a little bit, I think. So talking about galvanic cell, as I mentioned, there is a difference in electrical potential in a particular galvanic cell. And a volt is 1 joule of work per coulomb of energy. So that little conversion we'll use a little bit down the road there is a joule over a coulomb, basically. And if you're asked in a question, basically to calculate the cell voltage, the electromotive force, or the cell potential, usually what they're pretty much asking you to calculate is the cell voltage in that particular case. And as I mentioned, there's sort of a potential difference that allows those negatively charged electrons to kind of be pulled over. Here's actually a galvanic cell. Hard to see, but right there's the salt bridge connecting both of them. And here we got some positive voltage basically happening here. So another way that we can sort of represent a galvanic cell is through what's sometimes called the cell diagram. Sometimes people call it a line notation, but that is what this is over here. And basically, it always is sort of written like this: anode on the left to your cathode. And this is, there's a single line that separates the different phases that you have within the anode. So we have zinc, which is the solid electrode that's hanging in there, and we have zinc ions that are floating around in the solution. The kind of double line there represents the salt bridge. And again, we have another single line that separates out, again, sort of the different phases of our cathode. We have our copper ions floating around in the solution. We have our solid copper happening there as well. In addition, sometimes the molarity is given in these cell diagrams. And again, this is 1 molar. And that would mean that this is under standard type conditions. So remember, standard conditions basically is 1 molar if you're dealing with anything with concentrations, 1 atmosphere if you're dealing with pressures, and 25 degrees Celsius. So other things that could also be found sometimes in a cell diagram is sometimes there is not a sort of physical electrode, that metal piece that you could kind of stick into your anode or cathode side of your galvanic cell. So for example, hydrogen. They'll use something like platinum as sort of the solid electrode representative. Maybe graphite is sometimes used as well as that for those sort of anode or cathodes that really doesn't have sort of a metal type piece that can be used. Also, because sometimes the anode or cathode is a gas, you will sometimes also see pressure in the cell diagrams, and you'll also see, like I said, like platinum in there or something like that. Again, just being shown as the use of sort of the solid electrode. So how do you go from the cell diagram to like the equation? For the most part, when you look at a cell diagram, this is pretty much the way it's set up. First guy is a reactant, second guy is a product. First guy over here is a reactant, second guy is a product. So as you can see, zinc reactant, zinc product, copper 2 reactant, copper solid product. So it's kind of like reactant product is typically how they are written in the cell diagram. And that's how you could go from, say, the cell diagram back to the equation, obviously, and back and forth. Any questions on that there? But it's always anode to cathode, so always oxidation to reduction, kind of like how the cell is typically set up. Now, when we deal with galvanic cells, there's a type of reaction that we oftentimes deal with and we look at, and this is what is known as a standard reduction potential. And a standard reduction potential is sometimes abbreviated SRP for standard reduction potentials. And much like the name implies, they are reduction reactions. So they're all written as reduction reactions. We're going to see a table shortly. And when you look at this table, every single one of those reactions are basically written as reduction reactions, which means our electrons are on our reactant side. And that's problematic in a sense because we know we have an anode, which is an oxidation, and we have a cathode, which is a reduction, which means when we go to that table, one of the reactions, which is the anode reaction, is actually incorrectly written based on what is happening in the cell. It's written as a reduction reaction, but it actually should be a oxidation reaction. Now, the cathode reaction that you find on that table will be written correctly because it's a reduction reaction, so it'll be perfectly fine. So if we look at this cell here, and in this case, our zinc is our anode, and in this case, it is hydrogen, which is a gas, is our cathode. And as you can see, sort of the physical electrode that's being used in this case is the platinum wire. And we got a little hydrochloric acid, which clearly will supply H plus ions in that solution. And obviously here our zinc with a 2 plus. So ideally here, same thing happening. This guy's jumping out, electrons are coming over. This guy is going to combine with the H plus and make hydrogen gas, hence the bubbles that you see in the actual compartment over there. So that's what we see here, going from 0 to +2, being oxidized. Hydrogen going from +1 to 0, becoming more negative and being reduced in this case. Here's the cell diagram for that, and we can see, again, as I mentioned, reactant product in this case. So zinc a reactant, zinc 2 plus a product, H plus a reactant, and H2 a product. We also see a couple of other things inserted in here. We have the pressure of our gas because it's a gas also at 1 atmosphere, which means we're doing it under standard conditions. And we also have the addition of the platinum wire in there that's acting as the physical sort of electrode for our cathode side of the reaction. Any questions on that there? Now, how do we get these figures that when we look at this table for these SRP sort of reactions? Well, much like most things in chemistry, we usually will assign something to act as a standard to compare everybody else to. And for SRP or standard reduction potentials, they chose the hydrogen electrode, and it's sometimes referred to as the standard hydrogen electrode, or just referred to as She for the standard hydrogen electrode. And they basically gave it a value of 0 volts. So they kind of chose this guy as the standard, and they gave it a voltage of 0. This again is a reduction reaction as it's written, as our electrons are being added to our hydrogen. So now that they have sort of the standard that they could kind of compare everybody to, frankly, they just need to build some bunch of galvanic cells and get some cell voltage, and they could actually calculate the SRP values for pretty much everybody else along the way. And the way that they do that, for example, here, if we take the zinc here, which again in this case is going to be our anode, and the standard hydrogen electrode as our cathode, and they hook it up here, they actually get a cell voltage for this cell of 0.76 volts. Now, they could actually use an equation here, which is a good equation, and that is E of the cell is equal to E of the cathode minus E of the anode. So I'm going to say this now, and it may not make sense to you, but a little bit later on, hopefully it will. The purpose of this equation when you take your cathode minus your anode is if you go to the SRP table where you would find these values, every single one of them, again, as I mentioned, is written as a reduction reaction, which means in theory, what you really should do for the anode one is you need to take the reaction there and actually reverse it. And when you reverse a reaction, this SRP type reactions, what happens with the cell voltage is the sign changes. And you should change the sign when you do that. So if you do not want to worry about having to change the signs when you go to that table, you should subtract the values. And the purpose of the subtraction there is it will actually change the sign for you. Now, if you want to do it, I guess you could say more correctly, I guess, in a sense, and you want to change the sign for the anode reaction that you find in the table, you should add them and not subtract because you already did that part yourself. So there are two sort of versions of this equation. I personally, a lot of times, will use the subtraction version, but people will sometimes be taught the plus version. So the difference here is you change the sign. On the anode. Here you do not change. So I would say as we get going into this chapter, you probably should maybe just kind of choose one way and go with it because you don't want to kind of mix the two because you'll change it and then unchange it by subtracting, for example. So if you do that, if you want to change the sign, then add the values together. If you don't want to change the sign, just go to the table, take the values just as they are, and subtract the cathode from the anode, and it'll change the sign for you. But don't do both. All right, so in this case, when they use this equation here and they set it in, they're able to come up with the SRP value there for zinc as being minus 0.76. So again, here we have our cell voltage minus our cathode, which is 0, plus minus our anode in this case, moving the negative to the other side will get us our negative 0.76. So here's a table similar to the one you have in your book. I think yours is a little bit longer. We'll take a look at yours and again. But if you look at all these sort of reactions here, you can see that they are all basically reduction reactions. So what I'm talking about when we talk about sort of, should you change the sign, add or subtract, is this. If we look at, say, our original sort of cell that we looked at, which was the zinc, was our anode. And it was copper, I believe, in that one, which is right about there. And our copper, which was our cathode, for example. So when we look at these reactions and we pull out these guys here, we will have our copper plus our 2 electrons going to our solid copper, and our SRP value 0.34 volts. Now, if we take our zinc plus our 2 electrons gives us our zinc, our E for that guy, minus 0.76 volts. So as we know, the copper in what we were looking at earlier was our cathode. So that reaction is fine. It is exactly the way it should be. And it is exactly written as a reduction reaction, just like we find it on our table. Now, this one is technically our anode. And that one is not written from the table as an anode reaction or oxidation reaction. It is written as a reduction reaction. So technically speaking, we should reverse this reaction here. And we'll have zinc going to zinc 2 plus 2 electrons. Now, when we reverse that reaction, technically speaking, if you want to give sort of the right cell voltage for that, the sign should change. to positive 0.76 volts, as opposed to negative over here. So if you were going to flip the sign and you basically flip the sign on your anode, when you would go calculate E of the cell, in this case, you would take E of the cathode plus E of the anode because you already flipped the sign yourself. And that would give you, in this case, basically our 0.34 volts plus a 0.76 volts. And that's going to get us here 0.34 plus 0.76, 1.1 volts, right? Now, if you were just going to calculate, for example, just E of the cell and the cell voltage, and you knew which one's your cathode and which one's your anode, and all you wanted to calculate was basically E of the cell, you could use the other equation there, which is the same one, where we take E of the cathode minus E of the anode. Now, in this particular case, I'm not going to change the sign because I'm going to subtract, which means I'm going to get 0.34 volts minus a minus 0.76 volts. That subtraction will turn the sign for me, and we will end up with 1.1 volts in this case, which is the same. So that is what I was talking about earlier, that, and it's really your preference, whichever way you want to do it. So if you want to change the sign for the anode one, then you should take the two values after you change the sign for the anode and add them. If you don't want to worry about changing the sign or that type of situation, and you can still identify what's the cathode and the anode, then you can simply just take the values from the table and subtract cathode from the anode, and the subtraction part will do the sign changing for you. So it's your preference, but again, don't do both together because it will not turn out so well. Any questions on that? With that being said, if you were asked a question, for example, of you have this anode reaction here, and what is the cell voltage for it? The correct number should be the positive 0.76 volts based on the way it's written. Just like if you had a reduction reaction that involved the zinc, the correct SRP value there would be the minus 0.76 volts. So if you are going to write a half reaction and sort of asked to give either the standard reduction potential, or sometimes people call it the standard oxidation potential, you should give the proper sort of value based on how you wrote the thing. Any questions on that there? Yeah. So let's see here. Maybe I'll go. There you go. And here's again another table, but let's look a little bit more at some of the things that we find in this table and some of the things that we might need to do from this table. Here's a very small one as well in terms of the table. As I mentioned, the E is for the reaction as written. So as I just mentioned, if you are sort of writing the anode reaction, you really should adjust the sign for the E because that's the way you wrote the reaction. The more positive E value that you find on this table, that it has a greater tendency for that substance to be reduced. So sometimes in problems, they frankly don't tell you what's going on. They just say, hey, you built a galvanic cell out of these two things. And you need to figure out, what is your anode, what is your cathode in that particular case. And the way that you can figure out which one should be your anode and your cathode in that case is the one that has the more positive E is a greater tendency to be reduced. And when we talk about anode and cathode, it is the cathode that gets reduced. So if you're simply given just that sort of information of you built this galvanic cell out of these two things, which one's your anode and cathode, the one that has the more positive SRP value should be your cathode, and the other one should be your anode. Now, there should be a little asterisk on that, which is if they actually do give you an equation of what is going on in that problem, or they tell you in words of like how things are reacting, you should look at the equation and you should figure out what is being oxidized and what is being reduced. And then that's how you should determine your anode and cathode, which may be different than what the more positive one is. But lacking any of that information and just simply these are the two things you built the cell out of, and you want to choose one that's going to give you perhaps a spontaneous reaction and going to be at some positive voltage, take the one that is more positive as your cathode. That's going to create the proper sort of pull for those electrons to go to the other side and get you probably a pretty good functioning galvanic cell. The half reactions that we see in here are reversible, as I just talked about. So pretty much every anode reaction needs to be reversed if you're going to sort of balance the equation, put them together correctly. When again, you do sort of reverse a reaction, as we just talked about, you do need to change the sign. So if it's positive, it'll become negative if you reverse it, and vice versa. If it's negative, it'll become positive. Now, one thing that does not affect the SRP value that you find in that table is, as we know, when we have a half reaction, say like our zinc there, and maybe we need 2 of these guys or to get the 4 electrons. We have to multiply the half reaction by 2 to get us to the same number of electrons in each. This is one of the few things that you do not multiply the E value. So it will not be affected by any of that situation. So if you needed to multiply a half reaction to get the right number of electrons in each of them so that you could add them together and everything cancels out correctly, you actually do not need to multiply the SRP value or the E value there by the coefficient or the number that you did there. So that's a little bit different. It's unaffected by it. It'll basically be the same. All right, so why don't we try one here? Here's a couple SRP sort of things from a table. Take a moment here. Calculate the EMF or the E of the cell in this case. And why don't we also balance the equation as well? All right, ID the anode and the cathode as well. All right, take a few moments there, see what you come up with here. Okay, so let's take a look at this one. So the first thing here, we are not really told sort of what's going on here, so we do want to look at the SRP values. And again, if they were not provided, you would have to go to the table to find these 2 guys. And we're going to be looking for the one that's more positive, and that should be our cathode, which means in this case, even though they're both negative, that one is more positive, I guess. And that should be our cathode, and this should be our anode. Now, technically speaking, since I did ask you to balance the equation, that means that the bottom guy should be really the equation that you're going to reverse. So if we take our top guy there, it should be fine. And if we take the bottom guy, we're going to reverse it there. And goes CR3 plus and 3 electrons. We also need to, in this case, since we did reverse it, technically we can change the sign there to plus 0.74. We also need to make sure we actually have proper number of electrons in each of these, right, before we add it back together. And in this case, the common number there is going to be 6, which means really, in addition here, I just need to multiply the top guy by 3. And I do need to multiply the bottom guy by 2 to get us to 6 electrons in each of them. So with that being said, let me do that and pop those in. And if I do that there, multiplying the top guy by 3 gives me 3, gives me 6 electrons and 3 of those. Multiplying the bottom guy, 2, a 2, and a 6 in this case. Remember that although we did multiply by these numbers, these guys are unaffected by that, so you don't need to multiply or do anything with that. That then should give me my proper equation here, where the electrons should completely cancel out. Gives me my 3 cadmiums. If I wrote that right there, try that again. There we go. My 3 cadmiums there, plus my 2 chromiums, going to my 3 cadmiums on the right and my 2 chromiums there on the right hand side. Now, in this case, when we go to calculate E of the cell, we do have two options. Since I actually did, in this case, switch the signs, again, I'm going to add them together instead of subtract. So I take 0.44 volts plus a 0.74 volts. That's going to give me a 0.34, I think. So that's 4. There you go. So 0.4 minus 0.74, get the right numbers there, 0.34 volts. Now, again, if you wanted to, you could have, like the question was asked pretty much, what is the cell voltage? You could have just went to the table. Once we've identified the cathode, pop the cathode in there, minus the anode, which I do not change the sign because I'm going to subtract here. That will change the sign for me, and we'll get, again, the same value in this case. So to change the sign, add, don't change the sign, subtract, choose away. Any questions on any of that? This is a positive voltage, which is really good, kind of spontaneous type situation happening when you get positive voltage. Negative voltage, not so good, right? Any questions on that there? Yeah. All right, so let's try this one here. Galvanic cell consists of magnesium and silver. Calculate the cell voltage in this case as well. All right, so on this one here, we are trying to find our E of our cell. By the way, the 1 molars here, not really needed. They're really just there to tell you that it is under standard conditions, as we talked about. So in this case, if they weren't 1 molar, you would have to do something different, which we'll talk about a little later on in this chapter. But that's really why the purpose of that's there. And obviously 25 degrees is standard sort of conditions. And that's what the SRP table is under, these sort of standard conditions. So that just lets you know that, you go to the table and we're doing under standard conditions. Here, we're not really told what's going on. So again, we're going to go with the more positive as our cathode, which would be the silver in this case. And our anode would be the magnesium. And if we just want to calculate the cell voltage, once again, you could just roll with the subtraction version. And all you would have to do, again, is as soon as you identify it like that, you just pop in the number 0.8 volts minus. And again, I'm not going to change the sign because I'm subtracting. And that's going to give you 3.17 volts. Now, if we were going to sort of add everything together and rearrange things, we would need to flip our anode reaction, and that would give us magnesium goes to magnesium 2 plus and 2 electrons. That will then turn our sign for this guy to a positive 2.37 volts. Our silver would need to be multiplied by 2, so we have the same number of electrons. Gives us silver plus 2 electrons goes to 2 silvers. The electrons there would cancel. That would stay the same. At that point, that would give us our balanced overall reaction of magnesium plus a couple of silver ions going to magnesium ions and silver here. And again, here, since I did change the sign, I could simply just add these together and I'll get the same 3.17 volts as my cell voltage. Any questions on that there? All right. So again, in a problem like this, where really you're just looking for the cell voltage. Sometimes it might be quicker just to take the number from the thing and subtract it. But again, you could also just flip the number and add it pretty easily as well. All right. So when we talk about cell potential, it's also sort of going to relate it here to our thermodynamic property, which is our free energy. That's our delta G, if you remember, Gibbs free energy. And the work that can be accomplished when electrons are transferred through a wire from one point to the next is a thermodynamic sort of force. 1 joule work is produced or required when a coulomb of charge is transferred between 2 points in a circuit. And ultimately, in terms of the G, the maximum amount of work that can be achieved is equal to really the change in free energy. So remember that free energy is energy available to do some type of work. And we can use it to run something like a motor, like I said, battery type of thing. are basically these type of galvanic cells. So let's look at the relationship between our cell voltage and our EMF of our cell and some of these thermodynamic properties and take a look at these guys here. And we'll talk about each of them here. All right, so we can take our delta G and it will equal to minus NF of E of the cell. Um, F here is Faraday's constant, and we could use 96,500, or some people use 96,486, and that is a joule per volt per mole, or a joule over volt is a coulomb, which we'll see a little later on in the chapter towards the end. We talk about electrolysis, so that's also sometimes used. E of the cell here is still the same as we've been talking. So however you want to do that, that is the cathode minus the anode. N is the number of moles that is being transferred. So when we look at a half reaction, for example, like our zinc and our copper, and one's a half reaction, oxidation, and reduction half reaction. When we would go to get N for this reaction, N would actually equal 2. So it would not equal 4. You don't add them together. It's basically the number of electrons that's being transferred from the anode or the oxidation to your cathode. So that's what you're looking at, the kind of balanced number of electrons that are being transferred. So you don't want to add them together. You just want to take the balanced number in each half reaction, and that's what your N value would be. And it is negative Fe. So this is also why a positive cell voltage is good, because N is a positive number, F is a positive number, and if you get a positive number for E with this negative in front, that's going to turn your delta G into a negative, and a delta G that's negative is a spontaneous reaction, right? So also why if you get a negative cell voltage, not so good, because a negative voltage there, positive, positive, negative, two negatives make a positive for your delta G. So if you get a negative cell voltage, you basically just made a non-spontaneous sort of situation happening, and your delta G will be positive, which means it pretty much will not work. Now, we could also relate our E of the cell to our equilibrium constant, because we can't go too far without it. And this equation right here is pretty much the equation that you would use if you have anything involving the equilibrium constant. And as E of the cell is equal to RT and F, the R here, though, is the gas constant with energy, so the 8.314 version of it. T is our temperature in Kelvin. N is our number of moles of electrons, and F is our Faraday's constant, and natural log of K is obviously K is our equilibrium constant, and this is still our cathode minus our anode here, right? Or E of the cell. Now, the two sort of equations down here are when you're at 25 degrees Celsius, pretty much all these guys kind of become constants. And you can reduce this equation down to 0.0257 volts over N, natural log of K, or 0.0592 volts over N, log of K. If you don't want to worry about these two equations, don't just worry about this equation and plug the numbers in, and it'll all work out the same. So just roll with the numbers in the top equation, don't have to worry about the two bottom ones. But sometimes people will use those two bottom ones, so in case you see it, that's sort of where it comes from. At 25 degrees, those three things kind of become constant values. I will say that depending on which one of the three maybe you choose to do a calculation with, especially if you're solving for something like K, and depending on how you round, when you take kind of the inverse of the natural log of that E, you might get a slightly different answer depending on your rounding that you do. But the like exponent part of the number usually will be right on, and the front part will be slightly different, maybe with a little bit of rounding, especially when you're kind of like taking the inverse of the natural log or things like that. Depending on the rounding, might be slightly different. This is our triangle of death over here. This is, if we left the E of the cell, we could use this equation here to get our delta G. We have our delta G, we could get our K by using this equation. And obviously if we have our K, we could go that way as well. So this is sort of our triangle that relates all these guys together. This was the equation that we saw in the previous chapter, delta G and K. And then obviously our cell voltage sort of relationship that comes in there. Any questions on that there? So as I mentioned before, you could also look at sort of this equation, and you could look at E of the cell and our delta G along with K. And all these things really should still sort of agree with each other. So as I mentioned a second ago, if we hit a positive value here for our E, with that negative, that should give us a negative value for our delta G. That means that really the reaction as it's written should be spontaneous. It should be heading towards the product side. And because it should be heading towards the product side, that means we probably should have more products than reactants, and we should have a larger value of K. So again, all three of those things should sort of agree with each other. Positive E, negative G, large value of K. And the opposite would be true again if you have a negative value for your cell voltage. That negative and this negative will turn your delta G into a positive, which means pretty much in that case, it's hanging out over there at the reactant side, and it's not really going towards the product side. And that would mean that you would have more reactants than products in that case, and you should have a smaller value of K. So again, all those things should sort of line up. Clearly, if you have a cell voltage of 0, you got not much going on there. So you'll have a K value perhaps of 1 as well. Products and reactants are sort of equally favored in that particular case. Any questions on that there? Okay, so let's take a look. In this case, they did give us an equation. So remember, we do want to look and see what's happening. So if we look at the copper here, it's +2. Iron is 0. Copper here is 0 on the right, and a +2. So if we take a look at our copper is starting at +2 and ending at 0. So it is becoming reduced as it's becoming more negative. And our iron starting at 0 to +2. So it is becoming more positive. So it is being oxidized. So in this case, the copper, which is being reduced, is our cathode, which does agree in this case with the more positive. So if you ignored that whole part of that, you got lucky in this case. Yeah, and you got the right one. Again, not always the case. So if they do give you the reaction, make sure you do take a look at it. In this case, we can figure out our delta G here, which is going to be minus NF over E. Our E is going to be our cell there, our cathode minus our anode here. And putting that in there is going to give me 0.34 volts minus a minus 0.44 volts. Once again, I'm not changing the sign. So I will just subtract here, and that's going to give me a cell voltage of 0.78 volts. My N here is going to equal 2. As I can see, it is balanced in both of them pretty much. So 2 is going to be our N. And again, our F is a constant 96,500 joules per volt per mole. That's pretty much all I need here. So my delta G will equal minus 2 moles, are 96,500 joules per volt per mole, and our voltage there at 0.78 volts. Volts will cancel, moles will cancel, going to leave us our units of joules here at the end, and that's going to give us a 2 times 96,500 times 0.78. Remember, it is negative here. That'll give us a delta G of 150,540, which is negative joules, or roughly negative 150 kilojoules, which is typically what delta G is given in kilojoules, right? First off, any questions on the calculation there? Things do make sense. Once again, we hit a positive cell voltage, which means we should expect a spontaneous reaction, right? Which this would be spontaneous in this case. And it would head towards our product side. And if we did calculate the equilibrium constant, we would expect it to be a large value, right? For K. Any questions on that one there? All right, so let's try another one here. Question is, will 1 molar nitric acid dissolve gold metal to form 1 molar gold-3 ions? There's some SRP values there on the bottom. Okay, so let's take a look. So in this case, my cathode is, what's my cathode? The second one here? Wrong. Yes. So that is wrong because the question asked, will nitric acid, which is HNO3, dissolve gold metal to form gold-3? So that tells me this guy on the wrong side. Yeah. So that actually has to be reversed. So in this case, my cathode, which is the nitric acid right there, is actually going to be the nitric acid. This is going to be my anode because that will give me the actual reaction that we're looking for in this particular case. So with that being said, we can calculate E of our cell as E of our cathode minus E of our anode. And our cathode in this case correctly here is 0.96 volts minus our anode. And again, here, I'm not going to change the sign because I'm going to subtract. And that's going to give me a negative 0.54 volts. With the negative 0.54 volts, I know that when I put it into this equation that we just looked at, that's going to give me a negative, and that's a negative, which will give me a positive delta G, which means the answer is no, it will not, right? Because it's a non-spontaneous process. Any questions on that? You could actually put the numbers in, the 3 for the moles of electrons, the 96,500, you get like negative 156 kilojoules, something like that. Or positive, I'm sorry, 156 kilojoules, which will not be good. Any questions on that? So again, really important to make sure you look at what's happening or read the question correctly so that you do set up the reaction correctly. By the way, this is how they test, right? Or used to test. If you do have real gold, they put some nitric acid on it. Yeah, if it's still there, you got gold. And if it doesn't, then you don't really have gold in that case, right? Like pawn shops used to test for like if it's real gold or not. All right, let's try another one here. What is the equilibrium constant for the following reaction? We got a little iron going to some silver. Here's the SRP values that you would find in the table for these guys. So see what you come up with here. Okay, so let's take a look. Once again, we are given the equation here, so we do want to look at it. So iron's going from +2 to 0, and silver is going from 0 to +1. It is the iron here that's getting reduced. It is the silver here that's getting oxidized, which means opposite of what we see here. Our iron is our cathode in this case, and our silver should be our anode. So again, you want to make sure that you do look at the overall reaction as they give it to you. We see as well when we look at our anode, we would have our silver going to silver plus an electron. We would have our cathode going iron 2 plus 2 electrons going to iron. And in that case, we do see that we do need to actually multiply this guy by 2. And that's important because now we can see that N will equal 2 in this case, and that's the proper number of electrons that we need. Taking our equation there, E of our cell will equal RT NF natural log of K. We got our N, F is a constant. Obviously, you need to go 25 plus 273 to get to 298. R is a constant, and we do want to make sure we use the correct version of it there. And we do need to calculate E of our cell. So E of our cell here going to be our cathode minus our anode. And once again, I'm not going to change the sign in this case. So we're going to go minus 0.44 volts minus 0.8 volts. Going to get us there minus 1.24 volts. Putting that into our sort of formula over here, 1.24 volts is equal to 8.314. Our 298 divided by our 2 moles and our 96,500 constant joules per volt per mole. Natural log of K. Cleaning up, actually what I'm going to do is just multiply this to the other side. And then when I'm done with that, I'm going to divide what's on top to the other side. So I'm going to take negative 1.24. I'm going to times it by 2, times it by 96,500, hit equals. I'm then going to come back and divide by 8.314 and divide by 298. That's going to get me a minus 96.595 equals the natural log of K. We're going to do a little E on both sides there to get rid of it. And that will yield me and I'm not really rounding on my calculator, so I'm just taking the whole number, 1.1 times 10 to the minus 42 in that case, yeah. Questions on that? Again, if you round it a little bit at this point, you might get a slightly different front number, but the back number there should be pretty much hit on the minus 42. Any questions on that there? This does make sense, as we would expect, perhaps, right? I got me a negative cell voltage, which means I should have a positive G, which means this reaction is non-spontaneous. And that means I should have more reactants than products, which means I should have a small value of K. And I would say that's a small value K. Yeah, so that all correlates together. Any questions on any of that there?